Good evening, everyone from Denmark. We are going to start our webcast right now. The very first thing I would like to say is that it is organized in association with Wearable Robotics Association. And the topic for today is simulations as a tool for human-centered exoskeleton design. Yes, so the program for today is like that. I'm going to give a very brief introduction, and after that I will give a word to my colleague Ananth, and he is going to talk about simulations and exoskeleton design. He will explain some of the basics of the technology used for the design. And as the most interesting point of this presentation, he is going to talk about some case studies. So the very first thing I would like to mention, the title says that simulations as a tool for exoskeleton design. So the class of simulations that we are going to talk about is called musculoskeletal simulations. And what it means, it means that it's a rigid body dynamics analysis which uses motion data as an input, motion data and external forces acting on the body. It is being sent to the any-body modeling system, and the virtual human model is being subjected to this motion and external forces. And as an output, we get internal body loads such as joint moments, muscle forces, joint reaction forces. But Ananth is going to cover this topic, so I'm not going to go into too much detail. But I would like to highlight some of the usage scenarios for any-body modeling system. So the main one is probably the movement analysis. So any-body is quite often used in the gait labs, where they analyze all kinds of movements like walking, stair climbing, and so on. It can also be used together with some external devices for product design optimization, and this is actually the topic of today. So it can be an exoskeleton or it can be a medical device. The principles are the same. It could also be used for ergonomic analysis. And as I mentioned, it can also be used with medical devices. So it can be directly used for surgical planning and outcome evaluation. And last but not least, it can also be used in the multi-scale simulation. So we can compute internal body loads and use them for further structural analysis. And this is a brief presentation from me, so I'm giving the word to Ananth, please.
Thank you for the word, Pavel. Please give me a minute just to take control over from Pavel fully. I hope you can see my webcam now. Well, so I think we are ready to get started with my half of the presentation. So I've divided the presentation into 3 parts, or acts, as I've called them over here. In the first act, we will talk about some pain points regularly faced by exoskeleton designers. And I'll introduce you to what exactly we mean when we say human exoskeleton simulations. And in the second part, we will introduce, we'll give you an introduction to how these human exo simulations are run in the any-body modeling system. And the third act will then deal with the case studies, the whole idea behind Act 1 and 2 is to motivate the need for this technology in the first place and how this technology works. And this will finally build up to the case studies. So with that, let's get started with Act 1, where we talk about the pain points and human exo simulations. Now, over here, let me start by talking about a typical exoskeleton design cycle. So one would start with a schematic design of the device that you have in mind. And then this would then be translated into a more detailed CAD model, which resembles the final end product. And once you have the CAD model, you're probably ready to have a physical prototype of your machine. And you may want to do some kind of experimentation with this, where you sort of try this exoskeleton out on actual human operators. And based on the observations you make from these experimental trials, you may want to go back and refine your design. So this is an iterative design process, and once you're satisfied with the state of the design, the designer can then go ahead and submit it for approval from some kind of a regulatory committee, if it's applicable. This is followed by manufacturing and sales to customers. Now, we like to define two main pain points, or two main types of pain points that most exoskeleton designers face in this design cycle. The first one comes over here in the iterative design process, and this pain point has to do with trying to reduce the time and costs that actually go into research and development. So each time you need to make a physical prototype or arrange basically arrange the whole setup for the experimental trial, there is time and money being invested. So one question is, how exactly can we minimize this? And the second pain point actually has to do with how can the designer prove the benefits and the safety of the device in question to the users. And when we say users, it isn't just limited to the customers. It could be the approval committee or worker unions in case you're trying to sell an industrial exoskeleton, or health insurance agencies. So being a company who manufacture software for human body simulations, a question that we started asking was, can computer simulations actually help in addressing these pain points in some way? And we feel that this can best be done by inserting a step of human exosimulation right before building the physical prototype. Now, in these simulations, you take a virtual CAD model or a schematic model of your exoskeleton, and then combine that with a virtual model of the human body. So, and then try to test the device out in this virtual environment. So what you would do in an experiment, you're now trying to recreate in your computer. And now the design refinement is done on this virtual model instead of the actual physical prototype. So by the time you get to building your first physical prototype, you already have a fairly well-refined model, which in turn should minimize the number of design iterations you need to run based on experimental observations. So this is how we believe that human exosimulations can satisfy or can address pain point 1. And then we have pain point 2, for which there are some outputs of the human exosimulation. And I know I'm being very vague at this stage, but please bear with me. But there are some outputs that you will come across in the next slides, which give you some kind of insight into the effects of the exoskeleton on the internal workings of the human body. So we believe that these outputs, which will be described in the next few slides, will help you in addressing pain point 2. Now, one thing that is very clear is, before we can fully understand how simulations can assist with these pain points, we need to first understand human exosimulation and its output in the first place. So let us zoom into this into the region of the design cycle that I've highlighted within the red box over here. Now I've just redrawn the boxes that you saw on my previous slide. I've just redrawn them over here, and I'm going to try and talk you through the typical workflow of a human exosimulation. So one typically starts with a conceptual or a more detailed CAD model of the exoskeleton. And this model is then assembled on a virtual human model, following which we run the musculoskeletal simulations, which Pavel introduced in his part of this talk. And these are the class of simulations run in the Any-Body modeling system. And these simulations give outputs which can be classified into 3 categories from the point of view of studying these human exosystems. So the first set of outputs has to do with human performance, and these are outputs such as the muscle forces, activities, joint forces, metabolic power, and so on. Then you have outputs relating to human exo interaction, and these are mainly the forces at the points at which the human and the exoskeleton are connected together. So this could be the forces in the straps and connecting pads and so on. And then finally, we have the exoskeleton outputs, which are things like the actuator forces and power and the kinematics of the exoskeleton itself. Now, these outputs that we see over here are the key simulation outputs that we get from Any-Body that will be of interest to us in this presentation. And you will see that these three boxes they'll keep appearing throughout the presentation. So it's just a good idea to take note of them at this stage. So now talking about the goal of this webcast, as I was trying to motivate a few slides ago, is to try and see how these pain points can be addressed using these simulation outputs. And this will again be a recurring theme throughout the course of the presentation, especially when we get to the case studies. But before we actually get there, it is maybe more important for us to understand how exactly anybody calculates these outputs, so as to develop a better understanding and appreciation for how this entire setup of human exosimulations work. So let me try to break down this step into further sub-steps. Now, let us assume that we're starting with a CAD model instead of a conceptual model in this case. And let's say the CAD model is made in SolidWorks. We do have a Anybody exporter for SolidWorks, which helps you translate the SolidWorks model into a format that is readable by anybody. And once that is done, you can combine the Anybody version of this exoskeleton with the human body model to create what we call a man-machine model. Now, this is just a term that we give when now beyond this point, the human and the exoskeleton are sort of treated as a single system, and they are simulated as to be acting as one. And that's why, and hence the name man-machine system. And so there are two steps in kinematics. So one is to actually assemble the exoskeleton onto the human body. And the second part is to impart a certain motion to the man-machine system, which is the motion you're interested in investigating. And once you have the kinematics in place, the next step is inverse dynamics, where you actually compute the different forces in the system. These would be muscle forces, joint reaction forces, and so on. And this finally results in the outputs that we saw in the previous slide. Now, if you want to refine the design of your exoskeleton, you may want to sort of tweak certain design parameters of your exoskeleton based on the output. So, for example, if you're trying to design this exoskeleton so as to minimize muscle forces during a sit to stand task, maybe one of the design parameters is the spacing between the 2 feet, which you could probably optimize so as to bring the activations down to a good minimum. So these are all the steps that we undertake in the Anybody modeling system. And we will look at each of these steps in greater detail. And this will form Act 2 of the presentation. Now, we'll take a look at both kinematics and inverse dynamics in more detail. So let us have a look at kinematics first. Let us see what exactly goes on inside kinematics. Now, step one, as I mentioned, is to assemble the exoskeleton onto the human body. And this includes creating constraints between the two at the required attachment points, and also aligning the joints of the human and exoskeleton wherever necessary. So this could be just aligning the positions of the joint centers, or it could be aligning the joint axes as well. So in Anybody, we actually have two sets of tools, which we call measures and drivers, that have been specifically designed for the purpose of assisting with such an assembly procedure. The purpose of or what the measures do are they measure specific geometries inside your model, and what the drivers do are that they constrain the measured values to either 0 or some function of time. I know that this probably doesn't make a lot of sense at this stage. So let us actually let's understand measures and drivers by using some examples. So in this case, let's say you want to connect the hand of the exoskeleton to the handle that you're seeing on the screen. The way you would do this in Anybody is to first create a measure, which is a model object that measures the distance between these 2 points, and then you would create a driver which constrains the value of that measure to 0, and this would result in the hand being attached to the handle, and this constraint will be maintained throughout the course of motion. So irrespective of how the other body parts move, this constraint will always be maintained. Similarly, if you want to align the hip joint of this exoskeleton with the hip joint of the human body, you would again use a measure to measure this distance, and you would then use a driver to constrain the value of this measure to 0, and this would again result in an aligned hip joint. Now, both the measures I've shown over here are measures of distance. You can see the vector d is a position vector in both these cases. But then you have measures for measuring the relative orientation between two sets of two coordinate systems, and measures that give you the position of the center of mass and so on. And you can actually put constraints on all of these measure values by using these drivers and actually create more realistic assemblies of your exoskeleton. So once you have the exoskeleton assembled onto the human body, the next step is to actually prescribe motion to this man-machine system. And this motion, there are two ways, or there are two broad categories in which you can prescribe this motion to the model. And the first one is by using motion capture data. Now, obviously, when you're designing an exoskeleton, or actually, let me start this way. Like when you're testing an exoskeleton, you probably have motion capture data with the exoskeleton. But when you're designing an exoskeleton, you probably don't have, you probably would have to, you would have to start with motion capture data of the target motion that you're trying to achieve. So that's what was done in this case that you see over here. So this is a sandblasting activity done by a factory worker. And this motion capture data was collected without the exoskeleton so as to form the ideal target motion for the man-machine system. Which is what, you would ideally want the person to function as comfortably as possible. So, and then you assemble, and then that motion was then imparted, given to the man-machine system with the exoskeleton assembled onto the human body. So this is one way, but then sometimes you do not have access to motion capture data. And for those cases, there are actually some ways in which you can get creative to synthesize simple motions in any body. Let us take an example where you're trying to create a simulation of this exoskeleton going from a crouched position to a posture where the person is fully standing upright. The way you would do this is again using measures and drivers. And so you would essentially start by looking at, So I need to point out that this red sphere that you see on this figure is actually the horizontal, or the projection of the center of mass onto the horizontal plane. So with that knowledge, let us go ahead and start creating some measures for the system. So I've chosen two measures over here. And again, there are no unique choices for these because it depends on the type of motion you're trying to impart. I've chosen one of these measures to be the knee joint angle given by theta. And I've chosen a second measure over here, which is the position vector of the center of mass projection from the center point of the 2 feet. So that is this vector d. And then I use drivers to constrain the value of these measures to 0. Or constrain the value of this measure to 0, which means that this driver essentially ensures that the center of mass always lies above the center point between 2 feet. So it's a simplified balance constraint of sorts. And on the knee joint angle, I give it a time varying driver so that the knee joint angle changes over time. So this could be a constant velocity driver or a more complicated sinusoidal waveform and so on. So this is what the resulting motion looks like. So that gives you a quick overview of how the different ways in which you can impart motion to your man-machine system. So now that we have our motion in place, the next step is probably to go ahead and run inverse dynamics, where we calculate the forces that accompany, or the forces which accompany the motion. Now, the goal of inverse dynamics, as I just mentioned, is to take the motion that you see in kinematics and then calculate the forces that are actually producing the motion. So in a way, you're trying to reverse engineer the forces based on the motion that you see, and hence the name inverse dynamics. And the goal of this step is pretty straightforward and simple. It is just to calculate all the forces in the system. So these could be forces in the human body, such as muscles and joint forces, forces in the exoskeleton, or it could be the forces at the human exoskeleton interface. But calculating these forces isn't very straightforward. And one of the main roadblocks that stands in our way is this problem of force redundancy in the human exosystem. To put it simply, it means that the number of unknown forces in the human exosystem are just far too many. Let us see what I mean. So this force redundancy manifests itself in many forms, and I'm going to give you two examples over here. The first of it is muscle redundancy. Now let us take a case where the arm is trying to maintain this posture while holding a weight. So this would mean that the muscles at the elbow joint should produce a torque that is given by the arrow that is shown here in the figure. Now, this torque can be produced by different combinations of muscle forces. For example, I could say that all the work has to be done by this muscle on the right, and the muscles on the left just don't do anything at all. So there's 100 newtons of force on the muscles on the right, and then 0 newtons in others. But alternatively, there is a different way of distributing these loads across muscles so that exactly the same posture and the same elbow joint torque is achieved. So this is the problem of muscle redundancy, because in the human body model, just imagine when you have hundreds of muscles, this becomes the problem really, really blows up. So how exactly do we figure out that one unique solution for muscle forces based on a certain posture or a motion? Problem number 2 is redundancy of human-exo interaction forces. So, for example, if you take the interaction forces at the thigh between the human and the exo, this could be a feasible distribution of forces that is consistent with the motion that is seen. But it's quite likely that there is a different distribution of forces, which is just as good at supporting or accompanying the given motion. So again, there are infinite solutions for the human exo reaction forces, just like with the muscle forces. So the problem of inverse dynamics boils down to how a unique set of forces can be predicted. So how can we filter through these infinite solutions and arrive at one unique solution? So to understand the solution better to this problem, let us look at this as a flowchart. We have motion at the top from kinematics, which we start with, and where we are trying to get to are the forces. And the problem is that for a given motion, we have infinite solutions for forces. And so in any body, we try to refine, or we try to sort of reduce these infinite solutions to one unique solution by using an optimization procedure. And this is what we use in the Anybody modeling system. Now, just one note that I want to make is please do not confuse this optimization with the optimization of design parameters that we saw. Now, this was a part of the iterative design process. The optimization that you're seeing on the right over here is, sorry if you got some feedback over there. We're having a small audio issue. Okay, so the optimization that you're seeing over here is actually, yeah, sorry, just lost my track of thought momentarily. So the optimization you're seeing over here is actually happening in here within inverse dynamics. So it's all within this black box. So just remember that this optimization is different from what you're seeing right now. So the goal of this optimization is to try and see how all these forces can be used in a way that minimizes muscle effort. And this is formulated as a mathematical objective function, and the human exo and the human exo forces are calculated accordingly. So now it seems like we've had a look at kinematics, we've had a look at inverse dynamics, and so we do now have some kind of an intuitive feel for how the kinematic and force outputs that anybody gives us are calculated. So with that newfound knowledge, I think we're ready to move into Act 3, where we look into real case studies involving, which are basically just research papers that have been published by some of our users. And that will sort of demonstrate how anybody can, and musculoskeletal simulations in general as well, can actually help you address your pain points as an exoskeleton designer. Now, we're going to be looking at 3 case studies in this presentation. The first 2 cases are cases by our customers. So these are based on research studies that were done at the universities. And the third case that we will be presenting will be an internal case. This was the internal study carried out at our company, Anybody Technology. And this third case might be particularly interesting because it will show you how you can quantify metabolic energy savings for your device by using these computer simulations. So the running theme throughout all these case studies, as I mentioned earlier, would be to see how the 2 pain points can be addressed by using the Anybody system outputs. So what we will be doing for each case study is to take the research questions that the researchers are asking, and we will be sort of putting them under one of these 2 categories as either addressing pain point 1 or pain point 2. And this classification is just rough and intuitive, so please don't read much into that. It's just to aid some kind of just some general understanding during the course of this presentation. So if you take a question such as how strong must my exoskeleton motors be, I have judged over here that this is a pain point 1 question, because this has to do with the actual design of the exoskeleton. And this can probably be answered by looking into the actuator forces and power of the exoskeleton as given by anybody. And similarly, this question over here as to the exo overloads the back can be addressed using these joint forces that you get from anybody. And this is essentially the format that you will see in which, or the format in which the results of all the case studies will be presented. So this is just to familiarize you with the themes that we're going to be following for the next few slides. So on that note, let us move on to case study 1, which is a passive arm exoskeleton that was designed by the research group of Dr. Xiaoping Bai at Aalborg University in Denmark. I would encourage you to go and give this paper a read when you have the time later. So the exoskeleton that they designed looks something like this. So it was a passive gravity compensating exoskeleton. And for those of you who are familiar with gravity compensation devices, the whole idea is to place some strategically located springs in your mechanism so that these springs effectively cancel out the feeling of gravity. So in a way, it assists your body to move against its own weight. And the main question, so this study dealt with the design of this exoskeleton. So this, what you're seeing right now, was the end product of the study. And one of the main research questions that was asked is, what are the ideal spring stiffnesses for this gravity compensating exoskeleton? So I'm going to first talk you through the methodology that was used in the study. And for this, let me first draw your attention to the flowchart at the bottom, which is nothing but the design cycle that we saw in the first few slides of my presentation. So as I talk you through the methodology, I will show you how the different steps that actually correspond to the different steps of the design cycle. So we will first start by looking at the users. So this device was intended for people with paralysis of the C7 nerve, and such paralysis causes severe dysfunction of all the arm muscles, and they were interested in creating an exoskeleton that assisted in drinking motions. So step 1, as we see in this flowchart at the bottom, is to create a schematic design, and that is exactly what they started with. I've marked out the springs in this gravity compensation mechanism. And once they had, and it was the stiffnesses of these springs that they were trying to calculate eventually. So they knew the positions, but they wanted to know the stiffness. And they then sort of created a more detailed structural model of this exoskeleton in SolidWorks, and then exported this model into Anybody and combined this with the human body model to create a man-machine model. Now, this human body model, the muscles were weakened so as to sort of emulate the injury patterns that you see in patients with this C7 nerve paralysis. And the kinematics of the man-machine simulation was said to be the drinking motion. And this was followed by inverse dynamics, where they calculated the muscle forces and so on. And they then ran an optimization using, in this case, they used an external tool because they wanted their own optimization. I think it was a evolutionary optimization algorithm, if I'm not mistaken. And the goal of this optimization was to tune the spring stiffness such that the muscle activity computed by, or the muscle effort computed in inverse dynamics, or computed by inverse dynamics, was minimized. Now, they quantified muscle effort by this quantity that we call muscle activity. So for those of you who aren't familiar with muscle activity, it's you can think of it as the percentage of the total muscle strength that is being used at a certain time instant. So for example, if I said that the activity in my biceps muscles was 0.5 at a certain time instant, what this means is that 50% of your total biceps muscle force capacity is being used at that time point. So this means that there is the maximum activation that can theoretically be reached is 100%. And we typically present these activations on a scale of 0 to 1. So the maximum activity would be 1. And the goal of this optimization, of course, was to minimize these muscle activities. And once they had the optimized spring stiffnesses, they actually went ahead and built a prototype of the exoskeleton. This is just a video showing what the kinematic motion looked like. So now, having seen the methodology of the study, let us actually try and look at the results that they came up with. So as I described in the earlier slide, I'm going to take each research question one by one. So one of the first questions they asked was, do these optimized springs actually reduce muscle effort at all in the first place? And I've classified this as a question that would be close to something that a designer facing pain point 1 would encounter. And they answered this question by looking at the muscle forces and activities from the any-body outputs. So what you're seeing over here are plots of the muscle activity without the exoskeleton and with the exoskeleton. Now you can see that without the exoskeleton, the muscle activity is actually in a range of around 20 to 25. So which means that, and given that the maximum activity allowed is 1, the drinking motion was practically impossible without the use of the exoskeleton. So it is just the simulation was able to sort of force its muscles to violate this maximum activity cap to just be able to sustain this motion somehow. But then when they used the exoskeleton with the optimized spring stiffnesses, the activity actually dropped all the way down, with the maximum activity peaking somewhere around 0.3. So so the answer to the question was yes, the springs did seem to indeed reduce muscle effort. They were then interested in looking at how the exoskeleton and human motions were coordinated. And for this, they looked at the kinematics of the human and the kinematics of the exo, again, outputs that you get from the simulation. And these were presented as joint angle values. The third, and probably one of the most important questions in that many designers who are faced with pain point 1, what they might be dealing with is, what is the maximum capacity of this exoskeleton that you have? So in this case, because it was a drinking motion, the question they had was, what is the maximum load that the person can carry in the hand with when doing this, when drinking? And again, you can see that there isn't any body output which explicitly gives you this answer on a platter. But they did actually figure out an interesting way to look at it. So they decided to again look at the muscle forces and activities. So what they did was they actually reran this drinking simulation, and each time they varied the weight that was being carried in the hand from 0.3 to 0.9 kilograms. And you can see that for the case when the weight was 0.9 kilograms, the muscle activity, or the maximum muscle activity observed over all the muscles, which is what you're seeing over here in this figure, over the course of the motion, the x-axis is time. So you can see that when the weight is 0.9, that is when the activity just punches this upper boundary of 1. So this means that in theory, anything above 0.9 kilogram would have been impossible for the human body to achieve. Not in theory, actually. Practically speaking, it would have been impossible to achieve. So you can say that the payload must be lesser than 9.9 kgs, maybe 0.8 to have a factor of safety built into it. So these were the questions relating to pain point 1. They also asked a question which I thought was an interesting question relating to pain point 2, which is when you're trying to prove the benefits and the safety of your device to users. So this was whether the exoskeleton is actually comfortable to use. And for this, they looked at the human exoskeleton interaction forces, and they plotted these over the course of the entire motion. So I think there was one point of contact. So if you look at the exoskeleton, it was attached to the hand, and I think these are the forces between the hand and the exoskeleton, and the force peaked at 11.2 newtons. So how do we know if this is an acceptable force? So for that, they actually turned towards literature where there were some reports of what is the maximum comfortable skin pressure for a human in the arm. And they then multiplied this by the total contact area between the exoskeleton and the hand. And this product came to around 16.7 newtons. And given that this threshold of 16.7 was greater than the forces that we were seeing over here, the device was deemed to be comfortable to use. So this brings us to the end of this case. And what I would like to point out is how the outputs of the simulation were actually useful for the designer to get a good idea of how the device performs, or firstly to design the device when they were optimizing the springs, and then get some idea of the limitations of the device, even before they manufacture the physical prototype. So on that note, let us move on to the second case study. Now this is a waist exoskeleton. So this was an active waist exoskeleton which used soft pneumatic actuators. And this exoskeleton was developed at the Nakamura lab at Chuo University in Japan. Again, a very interesting paper. I would recommend that you have a look at this after this webcast when you have the time. So this problem was slightly different from case one in that they already had an exoskeleton that was operational, and they wanted to evaluate the effectiveness of this exoskeleton using anybody. So you can see that the exoskeleton assists these stoop lifting tasks. You can see that as a person bends down, and when he picks up the weight, the pneumatic actuators in the back, they swell up and start producing force, and then support him through the process of lowering the weight, beyond which they go dead. So what they actually wanted to do in this case is they had two designs for this exoskeleton, an old design and a new design. And in the old design, what they had was you had the pneumatic actuator that was producing a force in this direction. The problem was that one of the components of these forces was actually was along the spine, or was along the longitudinal direction of the spine. And so they feared that this spine compression force would actually cause or could cause long-term health effects. So they created a new version of the exoskeleton with a force reduction mechanism. So this is the mechanism that you see, it's marked out in green. And this is essentially just, it's a flat spring which deforms and essentially absorbs the spinal compression forces. So there is no so one component of the force of the pneumatic actuator is eliminated in a way. So they essentially wanted to use anybody to compare these two designs and see what the benefits, what the pros and cons of each were. So the general question that they were trying to ask is which of these exoskeletons is actually safe for the user. So again, talking you through the methodology, the users being targeted were factory workers who engage in such stoop lifting tasks. They started with a schematic design of the exoskeleton, where they had models of the pneumatic actuator, as well as they had a force amplification mechanism on the hip or on the waist, which the purpose was to increase the momentum of the pneumatic muscle around the waist. And they used these schematic models to actually calculate the force exerted by the pneumatic actuator, the force exerted between the waist and the exoskeleton, and the force exerted between the thigh and the exoskeleton. So once they had the schematic design in place, they actually skipped the step of designing the CAD model and then moved down directly to the human exosimulation. Now in this case, what they wanted to do was they wanted to run contrary to the previous case where you actually you had a CAD model and you assembled the exoskeleton onto the human body model. They tried to do a much simplified version of the simulation over here. Simplified but yet very effective, and that's why I think this study is interesting. So they decided to simulate this motion of stoop lifting under three different conditions. Oops, the video for some reason isn't working anymore. Yeah, now it is. So the first condition was without an exoskeleton. The second condition was with the old design. So they essentially took the forces calculated from the schematic model on the left and applied these forces to the human body model. And this was the old design because you can see that the force of the pneumatic actuator up here actually has two components, one of which produces compression. And then they created a third simulation of the same motion. But in this case, they actually removed the compression force in order to simulate the effect of the force reduction mechanism. So once they had simulated all these three conditions, run inverse dynamics, they created or they actually conducted an experimental trial with the exoskeletons, and they measured EMG to get an idea of what the muscle activities in the spinal muscles were. So with that being the methodology, now let us start looking at the research questions that were being answered. one of the first questions that or one of the primary questions they were interested in was whether the new design actually reduces the spinal compressive force. And this can be considered to be more closely aligned with pain point 2, where they were trying to evaluate the benefits and the safety of their device. So for this, they of course looked at the joint reaction forces between I forget which pair of vertebrae they chose. And this is what the average muscle force, or not the average muscle force, I'm sorry. This is what the compressive force between these two vertebrae looked like. So I'm going to just talk you through these three different curves. The curve that I'm pointing out right now is condition 1 without the exoskeleton. And you can see how condition 2, which was the old design, actually increases the compressive force because of the way of the second component of the compressive component of the pneumatic force actuator. And then as in condition 3, which is where they were trying to simulate the force reduction mechanism, you can see how the compressive force of the backbone actually reduced, and in some cases, or for certain durations, actually fell even below the condition where no exoskeleton was used. So this was the joint forces. So it seemed like the force reduction mechanism was doing its job. But how exactly does this new design reduce muscle effort? Does it do a better job than the old design? For this, they looked at the average spinal muscle force. So again, they looked at condition 1, which had the highest muscle forces as expected, because it did not have any external assistance in the performance of this lifting task. But then what was interesting is that condition 2, the average muscle forces in the spine were actually lesser than that for condition 3. So what this means is, even though the new design reduced the compressive forces, it did not necessarily reduce the muscle activity. So maybe there was a marginally more effort that was needed in actually performing this task. But on the other hand, you sort of you could ensure long-term health. So this is where such results from simulations actually can help designers make decisions when it comes to deciding what they want to trade off. They verified this the effectiveness of the exoskeletons by using EMG. So again, for condition 1 without the exoskeleton, the EMG, the peak activity of the erector spinae muscle was higher than what you see for conditions 2 and 3. So unlike case 1, which focused a lot on pain point 1 questions, case 2 has demonstrated how simulations can be used to address pain point 2. So now we move on to the third case, which was an internal study done here at Anybody Technology. And the goal of this study was to design this very simple waist assist device. So this was a passive device that used a spring to assist in the same stoop lifting tasks that we saw in case 2. And the main question we were trying to answer is what is the ideal spring stiffness value over here, which minimizes the metabolic cost of the lifting task. Now, this seems like a really simple problem, right? It's a really simple mechanism, but you will see the hidden complexity and how simulations help you unravel it when we look at the results. So essentially what we're trying to do is we're trying to create a virtual, we're doing a virtual recreation of VO2 max measurements that you would otherwise be performing in a laboratory. So again, I'm going to quickly talk you through the methodology over here. I won't waste much time because I think all of you are quite familiar with this design cycle by now. The target user group being stoop lifters. We start with the schematic design which just had this conceptual spring placed at the hip. And this was then developed into a more detailed CAD model, as you see over here. And this was followed by kinematics of this lifting motion. So once this was done, we actually ran a parameter study in Anybody, where now a parameter study it's very close, but still different from an optimization. Now, the parameter study was done on the hip spring stiffness. So what it meant was the hip spring stiffness was actually varied in discrete steps, and inverse dynamics was rerun with each stiffness value. And the thing is, the difference between a parameter study and an optimization is that you don't really try to solve for the optimal value over here. You just want to vary the parameter and see what the outcome is. And in the next slide, you will appreciate why we didn't do an optimization and why we did a parameter study. So one of the main questions we were trying to answer is, of course, what does the exoskeleton reduce metabolic energy cost at all, and by how much? And we saw this as a question that is probably relevant both from the point of view of pain point 1, when you're trying to design the exoskeleton, as well as pain point 2, when you're trying to prove its benefits to your users. So for this, we of course looked at the metabolic power outputs given by the simulation. These are what the graphs look like. On the x-axis, you have the duration of the lifting task, and on the y-axis, you have the metabolic energy rate. Let me talk you through these curves. The first curve, which is the black one, is where the metabolic energy rate or the metabolic power as a function of time when there was no exoskeleton. The second one is when the stiffness, when you use the stiffness of 25. So we see already that the peak metabolic power has already dropped. And then it drops further when you increase the stiffness to 50 Newton. And sorry, I forgot to mention, all these units are in Newton meters per radian for the stiffnesses. But what happens beyond 50 is when I increase it to 75, it actually starts increasing again. So it seems like of the values that we've tested over here, 50 gives you the least, or 50 gives you the least metabolic cost. Now, it might be very tempting to say that 50, this is the solution that we are looking for, right? And this is probably what an optimization might have given us, maybe not exactly 50, something in that vicinity. But one very interesting thing that the simulation told us is that higher stiffness does not necessarily guarantee lower metabolic power. But the plot thickens. So we actually had a look at the human exo interaction forces when the spring stiffness was set to 50. And it turned out that some of the interface forces, especially there's a contact point between the exoskeleton at the chest, and the forces were the pressure was actually so high that it could potentially even constrict blood flow in some cases. So it turned out that of the values, the stiffness values that were tested, it was 25 Newton meters per radian that actually gave a nice comfortable value of the contact force at the interface. So what this tells us is that we cannot always blindly throw an optimization at every problem. Sometimes it takes parameter studies such as this one because the metabolic cost had to be combined with another criterion in this case, which was the human exoskeleton forces. So we then, what I'm showing you over here is the other results for when the spring stiffness was 25 Newton meter per radian. And you can see the reduction in metabolic energy rate in the curves. And these tables are interesting as well, because it tells you the exact percentage by which the cost is being reduced. So it tells you that metabolic energy cost in this case has been reduced by 20% for the box lifting task as compared to a case without an exoskeleton. And similarly, the joint reaction force between the L4, L5 segments in the spine was also reduced by 20%. So again, simulations can unravel unintuitive relationships between performance metrics. So I hope that by showing you these three cases, I've made an interesting case for simulations as being a solution to the pain point ones. So the two pain points that we saw at the start. So I hope I've encouraged you to try out these class of simulations in case you as an exo designer or maybe even a salesperson are trying to overcome these two issues. And the take-home message would be that, yeah, we tried this out with musculoskeletal simulations. So on that note, I'd like to acknowledge Dr. Xiaoping Bai of Aalborg University and Dr. Taro Nakamura of Chuo University for sharing the videos of the exoskeleton and the simulation. And on that note, I will give the word back to Pavel, who will then take us through some final words, and we'll then move on to questions and answers. Thank you.
Okay, thank you very much, Ananth. So I'm going to speak a little about a few resources while you ask the questions. So please type them in the chat box. We have a few questions ready, but first I'm going to talk about a few events and resources available to get introduced more with anybody and get in touch with us. The very first thing I would like to mention is that there is going to be another relevant webinar happening on 26th of April. It is called Model Validation Using the Anatomical Reachable 3D Workspace. It was supposed to happen in March, but we got recently some good news that it got to be a finalist of a competition at the Veracon. So they had to postpone the webcast because they needed to present this work first at Veracon. So secondly, I would like to invite to visit our website, so where you can find different events, dates, and a publication list. So as you can see on the screen right now, we have a publication list which contains most of the publications, or at least quite many, using anybody, and you can visit it and you can filter by different body parts, industry, research area, as you can see on the screen. So please try to learn a little bit about anybody. We'll be very happy to hear, and please ask us questions if any. The last point I would like to mention that there will be several events, conferences where we will be present. So the very first one will be in Scottsdale, Arizona. It's close to Phoenix. Our CEO, Joran Rosenkill, will be, yes, it's a Veracon 2018 conference. So our CEO, Joran Rosenkill, will be present. And please contact us if you would like to meet him. Here is the email. So it's sales@anybodytech.com. Please arrange a meeting with him. He will be happy to speak to you. And we will also be present at CMBBE 2018 in Lisbon in Portugal. So please also ask at sales@anybodytech.com how you can get in contact with us. And the last point is that we are going to have a PhD course organized by Aalborg University in musculoskeletal modeling. It's going to be an advanced course, but they are going to start from the basics and go all the way up.